Hello all, I am Nitish Deshpande, a fifth year PhD candidate at UC San Diego, supervised by Professor Robert Heath. Today I am going to share my research on modeling, analysis, and optimization of MIMO systems with reconfigurable antennas. Let's begin with the motivation of my research. Think about your iPhone. We only notice the wireless part of your favorite apps when the connection fails. But do you know what enables this seamless connection? We have likely seen cell towers disguised as palm trees. Let's look at what exactly is the structure of these panels on a cell tower. Each panel comprises a large number of tiny cells which radiate signals and beamform towards your smartphone. These tiny cells are called antennas. But just having an antenna is not enough. You need an entire radio frequency chain which consists of several power-hungry components. A few of them described here are digital to analog converters, power amplifiers, and mixers. As cellular generations evolved from 4G to 5G, the size of these panels increased and so did the power consumption due to the number of these components. One solution adopted in 5G was to introduce an analog block that could be either a phase shifter or a time delay or switch to create a hybrid architecture. This reduced the hardware complexity and power consumption compared to the traditional fully digital architecture. As we now go towards 6G, there is need to further reduce this power consumption. My research focuses on embracing reconfigurable antennas on the cell tower, specifically parasitic antennas. Let's look at this two antenna example. On the left, both antennas are active, meaning they are both connected to an RF chain. On the right, only one antenna is active and the other is parasitic antenna connected to a reconfigurable load. It is termed parasitic because it doesn't have a power-hungry engine of its own. Just as a biological parasite, which draws nutrients from a host, this antenna draws induced current from the mutual coupling with the active antenna. We have essentially enabled a reduction in the hardware by recycling the energy. So what's the catch? Let's discuss the beamforming challenge. Usually we can control the signal strength and phase independently for an active antenna. But in a parasitic element, the signal's magnitude and phase are coupled together. So in this plot you can observe this coupled magnitude phase constraint which complicates the beamforming optimization problem. That's where my research comes in. I will summarize the outcomes of my research. I have proposed physically consistent models that account for this parasitic array constraint. My second contribution is developing new algorithms to jointly configure the active and parasitic elements to maximize the data rate. Finally, I propose new array designs that effectively exploit the mutual coupling phenomena to have a balance between different metrics like throughput, array aperture, hardware cost, and power consumption. To summarize, my research ensures that your iPhone stays connected while keeping the cell tower power consumption reasonable. Specifically, our hybrid architecture achieves more than twice the energy efficiency compared to traditional arrays. Thank you for your time, and I hope next time you stream a high definition video, we appreciate the efforts of the wireless researcher to design these energy efficient reconfigurable arrays.